I'm actually really appreciative to go second. Little quick amount of participation from the group here. From the previous presentation or from your... Hello? Okay, I like this one. Raise your hand really quickly if you think you have a good understanding of what energy load shifting is, conceptually. Okay, we got about half the room. So very quickly, I'm going to recap what energy load shifting is in concept. Your energy provider is supplying electricity to you, and you are consuming it. And depending on how much you're consuming, it drives how much they have to supply, roughly. Depending on how much they have to supply, there is a peak hour. That drives infrastructure. What the capacities of their substations are, the capacities of their circuits, the capacities of buses and your nearby network and transmission lines. Those capacities drive cost, and that's what the energy sector is most concerned about. So they have two solutions. There's a supply-side solution and a demand-side solution. The demand-side solution is kind of ideal for the energy sector. They essentially look to the customer and say, you're the one that's making a mistake. If only you didn't use energy at that particular hour, that'd be great. And so that's kind of what energy load shifting is essentially you as a customer providing either a different activity, different technology, or some other intervention allowing you to consume electricity at different hours. So one more time, does everyone have a clear idea of what energy load shifting is, conceptually? I think I got less. All right, I'll work with that. So my name is Robert Good. I'm a research engineer with the Center for Water Energy Efficiency. We work right over there across the street with the Center for the Western Center for Cooling Efficiency. One of our main priorities as a center is the straddle between the energy center or the energy sector and the water sector and how their operations and their use impact one another. This presentation, looking at energy load shifting of water utilities and trying to understand if demand management can make a positive impact on the energy sector, is a really good keystone presentation to introduce our work and what type of impact the water sector can have on the energy sector. So very quickly, what I'm going to do is I'm going to walk through the problem. Why is energy demand management so important? I'm going to talk about how the water sector can actually shift and what type of technologies and operations they are incorporating to make these changes. I'm going to go over the work we performed, the results that we've, our initial results that we've collected, and how that's going to impact our future research at the center. So let's start with California's electricity grid. So we worked closely with the California Independent System Operator. They're responsible for the supply and reliability of electricity in California across transmission lines, so between major regions of California. So we contacted them and started analyzing their information in order to have an idea for what time periods are actually essential for that energy load shifting if a customer, in this case the water sector, wanted to participate. So generally speaking, you have supply, they go through transmission lines, and they go to you, the customer. You, the customer, pay a cost. Depending on who you are, what type of customer you're classified as, that rate may or may not be static. It may be dynamic, it may be predetermined hourly, it may be predetermined seasonally. It depends. How much you pay depends on how much you consume. How much you consume drives how much they supply. But those two curves are not always the same. Supply does not necessarily always match demand. So what happens in between? Two things primarily. One is called curtailment, otherwise known as scheduled curtailment. So they are planning ahead and they're saying, how much supply do we have control over? How much supply do we not have control over? For example, think of variable energy resources, solar and wind. They don't necessarily have control of how much that is supplying. So if those, plus how much they're controlling, add up to more than what's being demanded, it needs to go somewhere, either battery storage or curtailment. So that can be curtailed to, in most cases in California, Arizona. Now, let's say you've curtailed it, and you are now supplying what you believe to be demand. Is it perfect? Raise your hand really quickly if you think supply perfectly matches demand always. You're optimistic people. So generally speaking, supply does not necessarily always perfectly match demand. You can think of losses across transmission lines. You can think about heat gains in buses and substations. And then there's the undesirable occurrences of actual damage to infrastructure caused by oversupply or blackouts and brownouts caused by occurrences of undersupply. So let's start going through the information available from CAISO and understanding what time periods these things really take place and what you, the customer, can do about it. So what things are we really looking for? Peak demand, that drives infrastructure. That drives capital investment at the utility. High or negative electricity prices. CAISO typically sells their electricity minute to minute, and those prices change according to what they call a dynamic market. Sometimes there's an excess availability of electricity, and they'd like to not curtail it, so they make it cheap, extra cheap, maybe negative, just for you to take it so they don't have to curtail it. Scheduled curtailment, that's what I just spoke about. Unscheduled overgeneration, unscheduled undergeneration. After you've scheduled curtailment, you think you're right, you're wrong, and that's where that takes place. And emissions. The generation of electricity is associated to emissions. Those are being tracked by CARB, California Air Resources Board. So we collected a little bit of information from them and tried to understand how the variable emission rate is associated to the energy you consume and how that can impact energy load shifting. So, in the next few slides, green, there's going to be opportunities for you, the customer, to increase your demand. Red's going to be an opportunity for you, the customer, to decrease demand. And these are ways to benefit the electricity sector. I want to be very clear about that. So here, we're looking at the electricity pricing from CAISO. This is the wholesale price. You can imagine this is the price at which specific customers, mostly IOUs like SCE, SDG&E, PG&E, major electricity retailers, are purchasing electricity from the wholesale market. So what you see here are opportunities where pricing is excessively high, a magnitude 10 higher in some cases, during the peak hour. So hour ending 5 to give or take 8 p.m. There are also negative opportunities for pricing of electricity. That occurs more or less when the solar generation is at its peak. In California, there's a variety of solar generating plants and distributed generation. So negative pricing typically occurs when there's peak solar generation. So let's look at net energy demand. This is the actual supply of electricity that has to go over transmission lines. CAISO only really cares about that largest number. That drives capital infrastructure. And what we see is that is happening at a consistent hour, even though it's going down, so the state's getting better at it. But you'll notice as we introduce more renewables over time, going from 2014 to 2017, this hour doesn't move. So that's important. It's shifting a little bit, but that hour more or less is predictable. And that's important for you, the customer, if you're planning ahead. Let's look at curtailment. So they're planning their electricity supply. They might need to move some of it to Arizona. When does that actually happen? Pretty much exclusively during the hours of solar generation. Even though we do have wind supply, generally speaking, that's not getting curtailed. That's getting utilized near or at where it's generated. So primarily what we're looking at is solar generation is getting curtailed. Let's also look at over and under generation. So after you've curtailed, you've made a mistake. There's a little bit of a difference between over curtailment, supply, and demand. This is on the order, on the entire state of California, this is on the order of about 1 to 2 megawatts. So they're doing pretty good. But these hours where these things are occurring are relatively consistent. So we see patterns of undergeneration, overgeneration, undergeneration, overgeneration, and these are tied to ramping. As variable energy resources come online and come offline, you see ramping causing periods of undergeneration and overgeneration. Periods of undergeneration, that's these guys, you want to reduce your consumption because there's not as much of electricity available. Periods of overgeneration, that's these guys, you want to increase your consumption. That way, the overgeneration isn't really a problem. You've increased your demand. Another question is, we wanted to look at the variable emission rate associated to the energy you actually consume. Generally speaking, specifically at water utilities, if they were to ask their electricity supplier, hey, how much emissions are related to the energy I consume, they're going to give them a flat rate. Now that rate may be dependent on the week, month, season, or year, but they're going to get a flat rate across the day. it doesn't really help you if your priority is time of use energy load shifting, where I'm trying to look at the specific hour, not the specific week. So we had a suspicion. We looked at the way that they were calculating the emission rates of electricity production, and we noticed that all renewables are just given a flat value of 0. So what they've really done is they've linearized the association of emissions to energy production. So we thought, is it linear? It's linear. The association of emissions on a monthly level according to the actual ratio of renewables on the grid is a linear relationship. So we took that and we calculated the variable time of use emission rate of electricity supply on the California grid on average. So this starts to tell you that solar generation is really driving the intensity of carbon emissions associated to the energy that you, the consumer, are demanding the generation of. So what this is telling us a little bit, if you're environmentally minded, if you are a champion of sustainability, load shifting even a little bit into the middle of the day has a significant impact on your total sustainability. This can be a magnitude difference of 3 to 4 times depending on the region you are in California, depending on the availability of resources generating to meet you. So what does this tell us overall? What time periods should we really be looking at? Generally speaking, you want to load shift into the 10 a.m. to 5 p.m. period and load shift out of the 5 p.m. to 10 a.m. period. And again, this really comes back to it's driven by a combination of curtailment, excess supply, overgeneration, and undergeneration. And if you could load shift significantly enough into these periods, you would make a positive impact on the statewide energy grid. That's not to say that SCE and PG&E don't have maybe a little bit modified hours depending on their generation portfolio and maybe on the needs of their customers. But generally speaking, these are the hours that everyone understands load shifting is necessary. So let's shift the conversation a little bit and look at the water sector. What is the water sector doing? How do they operate? And what can they do to load shift? So our suspicion is this, that a water utility whose primary charge is to supply you, their water customer, water when you need it, how you want it, at a satisfactory pressure and a satisfactory flow, depending on maybe agreements to customers, agreements with cities, etc. We believe that with an offline analysis, so essentially a computer model that satisfactorily simulates the operations of the utility, we could demonstrate that they can load shift. We believe that with full automation, truly in the field, we would be able to load shift in addition to load ramping. The difference between those two are kind of minor, but kind of significant. Load shifting, kind of going back to the previous conversation, load shifting means I can permanently load shift some of my demand to a new hour, whereas ramping has to do with instantaneous, under 5 or 15 minute kind of scale, supply or unavailability of electricity. So kind of the difference between curtailment versus over and under generation. Over and under generation can happen moment to moment, depending on the availability and the demand. Curtailment is scheduled. It happens on an hourly scale. So for this study, we wanted to show that we could load shift. We could handle curtailment. The next step after this is over and under generation. So how does a water utility operate? Typically you have a source, it goes through treatment, you have a series of storage or reservoirs, and you have a distribution, lift stations, pressurization stations, pressure reducing valves, pressure reducing stations, all controlling the distribution and operation of water underground or overground as it gets to you, the customer. Now, there's two paths here. The customer, depending on what community you're in and how advanced they might be with their infrastructure, it may get treated and sent back to the environment, or it may get treated and used one or multiple times for, let's say, irrigation, golf courses, in some cases, agriculture. And then that goes to the same exact system, different tanks, different pumps, different pipes, but same concept until it goes through use. And this cycle can repeat, even if that arrow is not drawn here, that cycle can repeat as many times as the technology or the infrastructure will allow. So, what can we do knowing that system? Well, we know that if we don't want to change demand, it's not like we're going to the water utility and saying, talk to your customer and make them use water at different hours so that you can use your pumping at different hours. We'd rather do this all behind the cloak, Wizard of Oz style. We'd like to change how we actually pump, how we actually move water, when we fill our reservoirs, when we fill our tanks, when we pressurize our pipes, without impacting your demand. And our hope is that we can demonstrate that this is true and that we can essentially load shift when we operate our pumps, when we operate our tanks, without the customer knowing any different, but the electricity demand happening at the utility, the sum of all their pump stations, adds up to load shifting. So let's look and see if we can do that. What do we need in order to answer this question? What's the big data needs? What's the software we need to develop? So let's go through that. We need your GIS data. Where's your pipes? Where's your tanks? We need all your pump information. We might need to do a pump test. We might need to do a pump efficiency report. We need to have a little bit of information about your water customers. When do they want water? How much water do they use? Are they picky? Do you have a contract? Maybe you have a contract, Mr. or Mrs. Water Utility, with actually purchasing water certain hours. All this information needs to get collected. So, we need someone to collect it from. So for this particular study, we partnered with the Molten Miguel Water District. They are a Southern California water district. They supply water and reclaimed water to about 200,000 people in Southern California around Irvine, if you're familiar with the city. They're a very forward-looking water utility. They have well-maintained GIS, pump reports, customer information. They have a near fully SCADA-operated system for much of their new pump and pressure-reducing valve stations. And it's a generally complex station, meaning that the report we put together, the research we do, will be significant. Rather than just being a demonstration of a concept, it'll be the application to a very complex, difficult problem. So, how does the water utility operate? Can we build the computer model? Can we simulate that computer model and then make it match the real world operations? Let's optimize that model and then let's perform load shifting. So let's walk through it. How do we determine the operations? Kind of what I was getting at a moment ago. We need more information about your pumps. We need to know about your set points. What points do you like your tanks at? How much flow do you like coming out of your pumps? How much pressure do you like at different elevations of your customers? We need to know it. Purchasing, contract agreements, typical valve settings. You might have a pressure zone cut off from another pressure zone. You might have a tank that doesn't work anymore. We need to know these things in order to actually simulate it. Then we actually build the model. This is called an asset framework. It is an example of the type of connections you would see for a single pressure zone. So think of a single type or range of elevations that the water utility is serving. You might have connections to 1, 2 tanks directly connected to the pressure zone, 1, 2, 3, 4, 5, 6 different pressure zones, all being fed from or feeding to your pressure zone. You may have a very complex series of pump stations that are taking from groundwater, treating it, moving it to 2 separate pressure zones depending on the time of day, valve setting, demand, etc. So we build this information using the data that they just gave us. This goes into a computer model, a much more complex looking one than this, where it includes every individual junction, every individual pipe, every individual valve, every individual pump, and etc. Now we need to simulate it, and we need to calibrate it. We need to make this model that we just spent so much time making actually match the utility. So we do. So we get this high resolution information. It can come back at almost whatever scale we want. 1 minute, 5 minute, 1 hour, 1 day, for whatever duration we want. So for this particular application, we partnered with the utility. They provided us GIS data. We developed a hydraulic model that matched their system. That hydraulic model then reported what type of energy profile this water utility has at each individual pump station, what the water age is throughout the system. So we're able to track individual particles of water through the hydraulic model. What type of pressure, what type of flow is actually getting to customers. Now this is all great. We match the utility. We're able to show that their SCADA matches the hydraulic model. Good stuff. What's the next step? The next step is then say, let's propose new ways to operate. We know how you operate. We're able to simulate it. Let's change it. So we start saying, what if you didn't operate your pumps at all? Well, then we find out that they don't serve their customers. Okay, let's try another one. Let's see if we can instead operate all but one of your pump stations. Let's try various combinations. 50,000 to 500,000 to 5 million simulations later, and we start getting an idea of what type of pump stations are necessary, what type of tank levels are necessary in order to meet demand. So essentially what we're trying to get out of it is, what type of load shifting can this water utility particularly do, given their assets, given their elevations, given their customer profiles. For this, so a little bit of detail on the actual optimization we did. We found that the optimum duration of a simulation was 48 hours. A little bit longer, and you captured unnecessary data, and it just made the simulation take longer. Anything less than 48 hours in the simulation, in the attempt of performing an optimization, says, well, don't run your pumps. You have enough water in your tanks at hour 0, just drain your tanks, and by the end of 24 hours, you're good. But then you have no more water in all of your tanks. So 48 hours ended up being a good middle ground, allowing the water utility to really simulate operations, the importance of tank levels and reservoir storage, versus energy and cost reductions. Optimum resolution was about an hour. Again, this goes back to the difference between curtailment, overgeneration, and undergeneration. We are looking at curtailment, energy load shifting, rather than ramping. So 1 hour was an appropriate time frame for us. Variable speed drive pumps versus single speed drive pumps. So you have open pressure zones, which have connections to other pressure zones and tanks and reservoirs. Those typically operate with single speed drive pumps. Whereas you have a closed pressure zone, which typically means that there is no tank, there is no connection with another pressure zone, it's in and it needs to get consumed or else. Those are typically served with a variable speed drive pump. Those type of pressure zones and those type of pumps were not optimized as part of our study, because simply what you can do with those type of optimizations is reduce the set point of those VSDs. We weren't really interested in doing that. That's a different type of study. That's a pressure management study. So we put that off to the side for later research. And lastly, in addition to everything I just spoke about, we did want to answer the question of what type of impact water customers could have on the success of this type of program. If a water customer proposed, hey, I could stagger my use by 1 hour forward or 1 hour backward, does that help you, and will you help pay me? So we wanted to answer the question of, is there a benefit? So we'll start a little bit about what actually got included into the optimization. For those that are familiar, we used a genetic algorithm, specifically particle swarm optimization. We optimized for total cost. So we wanted to minimize total cost as a combination of energy cost, pumps operating, source water costs, which we didn't utilize in this. We just set that to 0, but it is part of the equation. We can use it in the future if we feel that there's a strong need from the water utility to include this. Asset activation. You can imagine there's a cost every time I want to operate a pump, close a valve, send an employee across town to go and open or shut off a pump station or shut off a pressure zone. There's a cost associated to that, and I can put that into the system, and we did. Operating penalties. This is the way the system optimization tool is able to come back and say whether or not this was a satisfactorily hydraulic solution. We essentially assign a penalty for every junction and every pipe and every pump if it does something we don't like. Is the pressure too high? Penalize it. Is the pressure too low? Penalize it. Is the flow too high? Penalize it. Is the pump operating too high? Penalize it. And we just keep doing that until it starts getting a bit better. Got it. So we target all the things that I spoke about earlier. We did it again for the shifted water demand profile. What happens if customers participate? This is what that demand profile looks like. So let's actually start getting into some data. I hope you guys like data. So the big black bar is the baseline operating conditions, the base calibrated simulation. This was for the reclaimed water supply system at this utility. A lot of their demand occurred during the night from golf courses and landscaping, so the energy supply typically matched with the demand supply. What you see below is the variety of simulations according to what type of energy load shifting we were promoting with that simulation. So we have existing, meaning we want to energy load shift, we want to minimize cost for your tariff, the current tariff you, Mr. Water Utility, are current under. Energy, minimize total energy use. I don't care where it came from, I don't care how, just minimize my total use. GHGs, minimize my emissions, period. Overgeneration and curtailment, targeting those. Try to consume curtailment when it was going to be curtailed, and try to consume overgeneration and remove yourself, load shift out from undergeneration. Now, I'm not going to go into detail about the success of each of these, but generally speaking, they did what they asked, more or less, and I will get to that more or less detail in a second. This is the same concept, the same plot for the shifted water demand. And what we really found was, and I'll go back and forth just in a moment, the lines between the optimizations spread out a bit more, and I'll get to that. But what it really comes down to is, when you have the shifted water demand, the peak water demand for this utility is a little bit lower because some water utility customer or water customers shifted up, some water utility customers shifted back. The peak demand goes down, we had more capacity to load shift, more capacity to decide how much energy we wanted to use at any particular hour. And that's the significance of this for the participation of water customers. So here's some of the data. I'm going to walk through it very quickly. So total water pumped, total energy consumed, and total emissions are essentially linearly related. We were able to demonstrate, without impacting your demand, that the water utility could pump less water. Essentially, they're moving water around because of the interconnectedness of their actual utility. They can move water more or less. That is a direct impact on how much energy they use and therefore how much emissions are associated with them. Next step, final storage difference. This was a variable that we utilized in order to understand the end of simulation water storage. So you have these reservoirs, you have these tanks. A water system operator is concerned. The more water in my tanks, the better. I have a better opportunity of operating my system in the future reliably because I have the water, it's available. I can end my simulation with less water in those tanks. That's going to have an energy impact. It means I didn't pump as much water. I didn't use as much energy, with the impact on reliability. This was part of the penalty weight process, trying to inform the hydraulic model to operate reliably, trustworthy. By the end of the simulation, have enough water. What we found is, despite how much we worked, water utility operations are finicky. If you're not extraordinarily careful with your operations, with your penalty weights in this case. What you can find are simulations that increase your total net volume by the end of the simulation by 6 or 7%. Base operations add almost 9% water. Some of these optimizations, because they're trying to promote energy savings, cost reductions, they say, why not just don't fill those tanks? And so they drain your tanks 8%, 16%, 30%. So by the end of a 24-hour period, you can have almost 30% less water stored throughout your system. That's a risk. If I were to go to a water utility operator and tell them, I know how to save you money. Stop running your pumps. Don't fill your tanks. Don't serve your customers. It's a great idea. They're going to look at me and say I'm crazy. And that's the truth. And what we found with this research is one of the takeaways is that our methodology for optimizing and the methodology utilized by the rest of the industry for optimizing water utility operations is a search-based algorithm, and it's susceptible to local optima, it's susceptible to infeasible solutions, it's susceptible to short-term solutions in favor of long-term reliable operations. And that's something that we learned that we're realizing the rest of the industry is not yet prepared to answer, which is why this technology, real-time operations of a water utility, hasn't yet kicked off. And I'll get back to how we think we can solve this. So what was the general takeaway of actually performing energy load shifting using this methodology with this water utility given their customers? Well, if they don't participate with their water customers, then we estimate they can save about 20% on their energy and 22% on their total emissions. And this is for a single demand profile, a single operating week, essentially. Additionally, if they were to operate with their water use customers, we believe that can increase by about 10% each. So this starts becoming significant, and the water utility has an opportunity to not only decrease their energy use, but to actually perform energy load shifting. And that's what these guys are capturing. Carbon intensity of energy demanded. If you start using that as an indicator, it tells you a little bit about the success of each individual profile in terms of how well it load shifted into or out of different time periods. And so what we're finding is, in both scenarios, the base situation, because it was trying to use more energy in the midnight time period and less in the middle of the day, since that correlated with demands, it has the worst carbon intensity for each megawatt hour of energy demanded. Different simulations such as GHG and overgeneration and curtailment did much better. There is one simulation that we found for the shifted water demand profile for the GHG optimization.